Welcome to this explainer. We are opening a pretty critical environmental case file today. The disruption of Earth's atmospheric shield. It's a fascinating, if alarming, story about invisible gases, broken chemical balances, and a stark warning coming straight from the skies above the South Pole. So let's jump right in.
Here is our roadmap for the breakdown. 1. The two faces of ozone. 2. A crisis of equilibrium. 3. Identifying the culprits. 4. The Antarctic anomaly. 5. Measuring the damage. And finally 6. The environmental stakes.
All right, kicking things off with Section 1, the two faces of ozone, or Earth's chemical duality.
Let's quickly establish our baseline here. You probably already know ozone is O3, a natural gas and an allotrope of oxygen. But what's really key for our investigation is its structure. It consists of 3 oxygen atoms bound together in a nonlinear fashion. And that specific, kind of bent molecular shape, that is absolutely crucial for how it interacts with light and protects our planet.
Now, ozone has a bit of a split personality, depending on where it hangs out in the atmosphere. Down here, in the troposphere, where we actually live and breathe, ozone is basically bad news. It dirties the air and actively helps form dangerous smog. But way up high in the stratosphere, ozone is the good guy. Because of that unique chemical structure we just mentioned, stratospheric ozone acts like a giant planetary sunscreen. It absorbs harmful UV rays and essentially protects all life on Earth.
Right, let's look at Section 2, a crisis of equilibrium, the broken balance.
For the longest time, Earth maintained this beautiful, perfect equilibrium between the natural formation and the natural destruction of stratospheric ozone. But, well, we broke it. The influx of foreign substances into our atmosphere triggered a massive destructive reaction. So now, the stark reality is that the rate of ozone destruction is vastly, vastly faster than the rate at which it's being formed.
And we aren't just talking about a minor atmospheric hiccup here. When you look at the atmosphere over the Antarctic, the numbers are just wild. 50%. That specific region literally lost half of the ozone that naturally occurred there. Half of the protective sunscreen, just gone.
But you know what's really crazy about this? Despite that massive global scale of destruction, humanity was completely in the dark for years. The actual realization of this extreme ozone depletion only came about in 1985. We were accidentally tearing a hole in our own shield, and we totally missed it until the damage was already profound.
So, moving on to Section 3, identifying the culprits. What actually caused all this depletion?
The investigation points squarely at 2 main chemical culprits. First up, chlorofluorocarbons, or CFCs. And everyday sources for these? Think refrigerants, aerosol cans, foaming agents, fire extinguishers, and solvents. Basically the stuff we used all the time. The second culprit is nitrogen oxides. These primarily came from heavier human activities like thermonuclear weapon explosions, massive industrial emissions, and agricultural fertilizers. These were the exact substances we pumped into the sky that completely wrecked the equilibrium.
Which leads us to a really fascinating geographic mystery in Section 4, the Antarctic anomaly.
Why did the South Pole get hit so much harder than anywhere else? Well, it's this compounding 3-step feedback loop. Step 1. Extreme cold below 20 kilometers allows polar stratospheric clouds, or PSCs, to form. Step 2. As ozone depletes in that environment, the air actually cools down even further. Why? Because ozone normally absorbs sunlight to warm the stratosphere. So less ozone means less heat, which creates even more freezing conditions for more clouds to form. And step 3, all of this happens inside a stable, long-lasting vortex of rapidly circulating air. It acts like a giant atmospheric fence, confining all that depletion right over the Antarctic region. To really grasp how bad this Antarctic anomaly is, you have to compare it to the North Pole. Both poles have these swirling vortices of air, sure, but their lifespans are totally different. The Antarctic vortex is incredibly stubborn. It remains completely intact throughout the whole polar winter and well into mid-spring. This gives those destructive chemical reactions months to just chew through the ozone. The Arctic vortex in the north, on the other hand, disintegrates much earlier, usually by polar spring in March or April, which stops the concentrated destruction in its tracks.
Okay, Section 5, measuring the damage, focusing on the science of observation.
You might be wondering, how do scientists actually track an invisible gas disappearing miles above our heads? They use a variety of highly specialized instruments to measure total column ozone. We're talking about the Dobson spectrophotometer, the M83 filter ozonometer, and the Total Ozone Mapping Spectrometer, or TOMS, which was famously mounted on the Nimbus 7 satellite. These incredible pieces of tech are quite literally our eyes in the sky.
Finally, let's wrap up with Section 6, the environmental stakes, looking at the real consequences of this depletion.
This atmospheric breakdown leads directly to a very severe physical threat. A decrease in total column ozone means an increased penetration of solar UVB radiation directly to the Earth's surface. Specifically, we're talking about the 290 to 315 nanometer wavelength range. This isn't just regular sunlight. This is the most highly energetic component of sunlight that actually reaches our planet.
And that energetic UVB radiation does real damage. This increased penetration has profound cascading impacts across the board. We're talking negative effects on human health, animals, and plants. It reaches all the way down to microorganisms, completely disrupting the very foundation of our food webs. It even degrades synthetic materials and significantly impacts our overall air quality. The loss of stratospheric ozone literally touches every single facet of our environment.
So, we've seen the chemistry, we know the culprits, and we've mapped this massive loss of equilibrium over the freezing Antarctic. Which leaves us with one critical, lingering thought to close out this explainer. With Earth's natural sunscreen actively depleting, how will our deeply interconnected ecosystems manage to adapt to the highly energetic, relentless threat of increased UVB radiation? Thanks for digging into this case file with me today. Keep asking questions.